Okay, let's start doing the homework. Homework number 5. So yeah, there are 10 problems in this homework. They're basically a revision, or just to help you recall some of the concepts. So let's start. So problem number 1: for the following elementary reactions, how are the reaction rates of each species related to each other? What is the reaction order? So again, these are elementary reactions. So elementary reactions makes things a lot easier in the sense that in an elementary reaction, your expression really corresponds to your reaction rate, unlike non-elementary reaction where your reaction, your stoichiometry does not represent your reaction rate. So just be aware of this difference. Okay, so let's go. So I have A plus 3B 2R plus S, 3A plus B 2R plus S, all these different types of combinations. Go to the whiteboard here, and let's start this homework. So this is homework number 5, CHEN 422, number 1. And these are elementary, so just remember that elementary, this means that your reaction rate corresponds to the stoichiometry, right? So just be careful about this. So basically, if I have 2A goes to B, your reaction rate is KCA squared, unlike non-elementary reactions where this is not true. So for non-elementary reactions, this is not valid really to write your reaction rate based on stoichiometry. So let's write the four equations. So I'm just going to copy them from here. 3A plus 3B is equal to 2R plus S. Right? A plus 3B, 2R plus S. And again, this is very simple, very, very basic stuff. 3A plus B, 2R plus S. The third one is A plus B, R plus 2S. And finally, this is the generalized one, AA plus BB gives me RR plus SS. Okay, so I'm going to do the generalized one, and you can do the other ones as you want. So we need to find two things. First one, how are the reaction rates of each species related to each other? So if you recall, it's going to be minus RA over A is equal to minus RB over, or RB over B is equal to R over R is equal to RS over S. Negative sign for reactants, and I have positive sign for the products. Okay, so just be careful of this. This is how you relate the reaction rate, and you can do them for all of them. So first one will be minus R over 1, 3, and all this stuff you can do it. Okay, and what's the order of reaction? And then recall, because it's elementary, your reaction rate will be minus RA will be K CA to the power A, CB to the power B, and your reaction rate is equal to N is equal to A plus B. Okay, so this is your reaction rate for the elementary reaction given the stoichiometry. Okay, this is number 1, very simple. I'm going to save this. I'm going to clear this, and let's go to number 2. Where is it? Wait. Sorry. Okay, yeah, sorry, I was having some technical issues. Okay, so let's go back to sharing the homework problem, or the homework. So problem number 2, write the reaction rate of A and determine the units of the rate constants for all the reactions in problem number 1. So it's just about determining the units. So let's let's if you recall from your slides, the number 2, the units of K, we can express them as time over concentration to the power n minus 1, or you can use time over concentration to the 1 minus n, right? So if n is equal to 1, the units of K is basically what? Just time, right? Sorry, we have an error here, just be careful. It's actually time minus 1, right? Time minus 1, so it's time over concentration, or time minus 1 over concentration to the n minus 1, right? Time minus 1 concentration time minus 1 concentration of 1 minus n. Let's just forget about this. Let me write them. Yeah, just be careful. Again, this is the type of thing which can easily be confused. I mean, with experience, or once you practice, I know that K, the units of K for n equals 1 is 1 over S. It's second minus 1. So it makes it easier, I guess, to catch these things, but let's try to do it properly. So time minus 1 concentration to the 1 minus n. So I can write it as time to the minus 1 multiplied by concentration to the 1 minus n, or we can rewrite it as 1 over time concentration n minus 1, right? Or we can write it as 1 over time multiplied by concentration to the n minus 1. So if n equals 1, K is S minus 1. If n equals 2, or it's basically time minus 1. If n equals 2, K will be time minus 1 over concentration of minus 1. So it's basically going to be, if we use standard units, it will be 1 over S multiplied by 1 over mole per meter cubed. So basically it's meter cubed per mole second. If n equals 3, K is going to be time minus 1 over concentration of 1 minus n, so 1 minus 3 minus 2. So basically it will be 1 over S multiplied by 1 over mole per meter cubed squared, right? Plus here, n minus 1 if it's at the bottom. So this will be meter to the 6 over second mole squared, okay? So this is, again, a very simple problem. Just, try not to, just be awake when you're doing these things so that you don't confuse these units. This type of thing is going to show up on the multiple choice if it shows up. Okay, let's save this. Let's move on to the next problem. So let me share the homework. Let's look at number 3. The pyrolysis of ethane proceeds with an activation energy of about 300 kilojoules per mole. How much faster is the decomposition at 650 than at 500? So again, this problem is also in your slides. So it involves the equation comparing the reaction rates. And this, you should expect this type of thing to show up. So again, you're given that pyrolysis, you're told the activation energy is 300 kilojoule per mole. You want to find how much faster is the reaction rate at 650 compared to at 500. So you're told that T2 is equal to 650 degrees Celsius, T1 is equal to 500 degrees Celsius. So the equation we're going to use, ln R2 over R1 is equal to ln K2 over K1 is equal to E over R1 over T1 minus 1 over T2, right? And we said a few things about this. First thing is that these temperatures have to be in Kelvin, they have to be in absolute units. I cannot use Celsius for these temperatures. This R is 8.31 joule per mole Kelvin. Again, be aware that's joule and this is kilojoules. So this 300 will be equal to 300 times 10 to the power 3 joule per mole Kelvin. T1 will be equal to, if I convert it to Kelvin, plus 273, we're going to get 293 Kelvin. 500 plus 273 will be equal to 773 Kelvin, right? So now it just becomes a matter of plugging in. So you're going to get 300 times 10 to the 3 divided by 8.31 multiplied by 1 over 773 minus 1 over 993. And again, be very careful. T1 minus T2 is also very common to get this wrong. And a simple thing to see, or a simple thing to know if your calculations are right or wrong, is just to look at your final answer, or look at this basically. As temperature increases, your reaction rate must increase, right? There's no way around it. If you substituted these two numbers incorrectly, you're going to see the reverse of this. So you're going to see, at the higher temperature, the reaction rate is actually smaller, right? So this means that you plugged them in the wrong order. And this is a common error as well. Just be careful with it. So if I do this calculation, I'm going to get what? The number I got was 7.59, and basically R2 over R1, if I take the exponential, will be about 1978. So, if I increase the temperature from 500 to 650, my reaction rate is going to increase by almost 2,000 times as much. Okay, so this is number 3. Let me save it. Let's clear. Let's go back to the homework. Number 4. Here you're being told that A decomposes by irreversible first-order kinetics. In a batch reactor, 35% of A is converted in a 7-minute run. When will it reach 85% conversion? And repeat this problem for irreversible second-order kinetics. So you're told you have an irreversible first-order reaction. You're being told that conversion is 35% after 7 minutes, and you need to find the time when the conversion reaches 85%. And then we will repeat the same thing for second-order kinetics. Okay. Let's go to the whiteboard and let's solve this problem. So number 4, in this case, you're being told it's a batch reactor, right? So we're really interpreting some batch reactor data. You're given some data for, point number 1, you're being told that XA1 is equal to 0.35 when T1 is equal to 7 minutes, and XA2 is equal to 0.85, and you need to find T2 equals what? You're being told that it's irreversible first order. So this corresponds to case number 1 from your slides. I mean, you can start with the IBR performance equation. For a first order reaction, you're going to get the same answer. But if you're given data for an ideal batch reactor, you can always use the cases as well to solve it. Same idea, the math is the same. But if you recall from case number 1, we already had this equation, so it makes things easier for us instead of rederiving it. Minus ln 1 minus XA is equal to KT. And you can rederive it as well from the batch reactor performance equation. So what I'm looking for T2. So let's plug in. So I'm going to plug in XA1 and T1 to get K, and then I'm going to use K and XA2 to get T2. So let's do it. So for 1, I said minus ln 1 minus XA1 is equal to KT1. So in this case, minus ln 1 minus 0.35 is equal to K into 7. So this means that K is equal to minus ln of 0.65 divided by 7. I'm going to plug this into the second set. So minus ln 1 minus XA2 is equal to K T2. So this means that T2 is equal to minus ln 1 minus XA2 divided by K. If I plug in these numbers, I'm gonna get what? So XA2 is 0.85, so I'm gonna get 7 ln 0.15 divided by ln 0.65, right? So minuses cancel out. K is 7 over 0.65, this is K, this is this number. And if I solve for this, the number I got is 30.83 minutes. And this is the answer for the first part of this problem, right? So basically, this is case number 1 for a first order reaction. However, you're also being asked to do it for a, if I go to the homework, repeat for irreversible second order kinetics. So I'm going to repeat the same thing for a second order reaction. I think this is page number 4. So I'm going to number them, page number 4. So now I need to repeat this for a second order reaction. Let me save this. Let me erase. Erase. And let's do it for a second order reaction now. Okay, so now I need to do the same thing for a second order reaction. So if you recall, second order, this is case number 2. And the performance equation for case number 2, where I have a second order reversible reaction, is 1 over Ca naught is equal, multiplied by XA, over 1 minus XA is equal to KT. And the same idea, I'm gonna use the first set to get K, and then I'm gonna use the second set to get T. Okay, so let's do it. So using the first set of, or the first piece of information, 1 over Ca naught into XA, XA1 over 1 minus XA1 is equal to KT1. I don't know K, I don't know Ca naught, I'm going to lump them, right? So just remember this type of manipulation. So XA1 is 0.35, 1 minus XA1 is 0.65, is equal to K, Ca naught, multiplied by 7. So K, Ca naught is equal to 0.35 over 0.65 multiplied by 1 over 7. Okay, so now I'm going to use the second set of conditions, 1 over Ca naught, XA2 over 1 minus XA2 is equal to K T2. I'm going to rearrange it, or, so you have T2 is equal to 1 over K Ca naught multiplied by XA2 over 1 minus XA2. And it's just a straight substitution. So this is equal to 0.35 over 0.65. This is 1 over K Ca naught here. Multiplied by XA2 is what? 0.85 divided by 1 minus XA2, which is, they do, yeah, 7 multiplied by 0.65. Yeah, so here I have a small substitution error, because 1 over Kca naught is 7.65 over 0.35, 7.65, 0.35, 0.85 multiplied by 0.15, and you should get T2 in this case to be equal to 73.67 minutes. Verify these numbers before using them. Make sure they're correct as well. So this is how you use the cases to interpret some batch reaction data. Is just plugging in the numbers, get familiar with the problem type, with the structure of these types of problems, because this is what's going to show up really on your test. Okay, let's save this. let me clear. Let's go back to the homework. Okay. Problem number 5, right? So after 10 minutes in a batch reactor, reactant with an initial concentration of 0.5 mole per liter is 55% converted. Is 55% converted. After 10 minutes in a batch reactor, reactant, let me just rewrite this. Reactant A is 55% converted. And after 27 minutes, conversion is 70%. Find the arete equation to present this reaction. So you're being told that at t equals 10 minutes, your conversion is 0.55. At t equals 27 minutes, your conversion is 0.7. You're given the Ca note is equal to 0.5 moles per liter, and you need to find the arete equation. So in this case, you don't know if it's a first order, second order, whatever. So this is case number 4, remember, when it's an unknown reaction order for the data. So let's solve this problem. And again, it's the same idea. So I guess this is page 6. This is problem 5. So in this problem, you're being told that Ca note is equal to 0.5 moles per liter. You're given 2 points. The first point at T1 is equal to 10 minutes. Your XA1 is equal to 0.55. And the second point at T2 equals 27 minutes. Your XA2 is equal to 0.7. Okay, so we need to find the reaction order. So if the reaction order is unknown, this is case number 4. And if you recall, the performance equation for case number 4 is Ca to the 1 minus n minus Ca note to the 1 minus n is equal to n minus 1 Kt. You can always use Ca and Ca note. However, I prefer to plug in Xa instead. It makes the algebra easier to plug in Xa. So if you recall that, Ca is equal to Ca note into 1 minus Xa, I'm going to substitute this guy here. So I have Ca note 1 minus n multiplied by 1 minus Xa to the 1 minus n minus Ca note to the 1 minus n is equal to n minus 1 Kt. All I did is I just put this expression instead of Ca and I distributed the power. I'm going to take Ca note out, so I have Ca note to the 1 minus n into 1 minus Xa to the 1 minus n minus 1 is equal to n minus 1 Kt. Okay, and this will be the equation I use. You can use this equation directly, but this is the performance equation basically for case number 4. Okay, so I will use this equation directly. So what do we want to find? We want to find n basically. Okay, so let's try to find n, right? So the way to approach this is as follows, right? You can plug in the numbers for XA1 and T1 and try to solve for n. However, it's gonna be a bit complex. You might get multiple solutions, but you want to really find the n which is gonna satisfy both cases, right? So in order to find the n which is gonna satisfy both conditions, I can either find a bunch of solutions for condition number 1 and try them all for condition number 2, see which one matches, or logically you're gonna combine both equations. So let's divide 1 by 2, right? So in this case, I'm gonna get Ca note to the 1 minus n into 1 minus Xa1 to the 1 minus n minus 1 is equal to n minus 1 Kt1. All of this divided by Ca note into 1 minus n 1 minus xa2 to the 1 minus n minus 1, and let's write this properly. I'm just dividing both equations. So this over this is equal to n minus 1 k t2. Okay, so this, by combining them, I can get the n which satisfies both conditions, both points, both experimental points. And I'm going to cancel n minus 1 by n minus 1, and this under the condition that n cannot equal to 1, right? N should never equal to 1 if you're doing this cancellation, right? Because if n equals 1 and you cannot cancel, you just the math is not right. You can't cancel 0 with 0. Okay, so just be careful here. And then CA note cancels with CA note, and I get this expression. So if I plug in all the numbers I know, so XA1, this guy is 0.55. I know this guy XA2 is 0.7. T1 right here, this guy is 10. T2, this guy is 27, right? So let's plug in the numbers. Little arrow here. So I have what? I have 0.45 to the 1 minus n minus 1 over 0.3 to the 1 minus n minus 1, right? Okay. Is equal to 10 over 27. If you cross multiply these guys, you're going to get 27 into 0.45 to the 1 minus n minus 10 to the 0.3 to the 1 minus n is equal to minus 27, 17, right? And from here it becomes an iteration problem or a trial and error problem. On the test, if this shows up, you just need to, try a couple of numbers and give me your best engineering estimate. So in this case, I tried n equals 2, I tried n equals 3, and I tried n equals 3.5, and I know that n is somewhere between 3 and 3.5. The exact numbers n, I think, is equal to 3.1 or something. 3.155. This is really the exact n, and this is your reaction order from which you can get your reaction rate. If you have a calculator, a graphical calculator, you can do this immediately. If you want to do it with Excel, go for it. Just send me the Excel after the exam. All this stuff, whatever works, just find the best tool that suits you. Solve these types of problems, okay? And again, the main idea here is that I'm dividing both conditions so that I can get the n which satisfies both conditions. Doing it with one condition will not work because, if I have a point, I can pass a million lines through one point. You're going to get a lot of solutions. I have 2 points. There's only one line through them. That's the idea of, dividing the two equations and finding the solution. Okay, sounds good. Let me save this page. Let me clear. Let's go to the next problem. Problem number 6. Okay. No differences between IBR, CSTR, PFR, which reactors are perfectly mixed. So perfectly mixed ones we said are CSTR and IBR. Which reactors are continuous? Continuous ones will be CSTR and PFR. Why are the performance equations of IBR and PFR very similar? Because an IBR behaves like a bunch of, or sorry, a PFR, a plug flow reactor, behaves like a bunch of ideal batch reactors in series, just plugging along. Define the following variables and list their units. So again, this is volume, meter cubed, liter, whatever it is. F, this is your molar flow rate, which is mole per time, mole per second, mole per minute. Small v is your volumetric flow rate, which is in volume per time. So it could be meter cubed per second, liter per hour, whatever it is. X is your conversion, it's dimensionless. Tau is your space-time, it's basically the time through which one volume of reactor passes through the system. Units are in seconds, and C is your concentration. Units are moles per meter cubed. Okay, just know this stuff. This is the type of thing which you probably see on a multiple choice portion. Okay, let's move on. Problem number 7. The reaction A goes to R with the following reaction kinetics: minus RA is equal to K, CA to the power N. Is carried out in a CSTR with a conversion of 60%, and CA naught is equal to 1 mole per liter. So you're given a reaction, you're given a reaction rate with an unknown order. You're being told it's being done in a CSTR, and you're being told that the conversion is 60%, and the initial concentration is 1 mole per liter. Okay, if the volume of the CSTR is doubled while keeping the same flow rate, determine the new conversion for N equals 0.5, 1, and 2. Okay, so you want to determine the new conversion after doubling the reactor volumes for different reaction orders. Okay, let's go to the whiteboard and let's solve this problem. I'm not sure what page is this. I think it's 7. If it's not 7, then, you know, it's not this. Okay, let's do 7. So you're being told it's a CSTR. And you're given some information, specifically that XA1 is equal to 0.75, right? Let me double check these numbers. 0.6, sorry, in this case. So in this case, XA1 is 0.6. V2 is 2 V1, so V2 is twice the volume of V1. CA naught is 1 mole per liter, right? So CA naught is equal to 1 mole per liter. What else am I given? Am I given anything? Yeah, I'm being told, yeah, V2 is equal to 2 V1. And I'm being told for N equals 0.5, 1, and 2, right? For N equals 0.5, 1, and 2. And I need to find basically XA2, right? XA2 equals 1. So let's go back to the problem and make sure we're able to get it correctly. I have A equals to R, reaction rate minus R is KCA to the N. CSTR conversion is 60%, CA naught is 1 mole per liter. If the volume is doubled while keeping the same flow rate, determine the new conversion at N equals 0.5, 1, and 2. So I'm looking for XA2 at N equals 0.5, 1, and 2. Conversion is 0.6, CA naught is 1. Okay. And we're also being told that minus RA is equal to K, CA to the N. Okay, so for this type of problem, starting point is always your PF or CSTR performance equation, right? CSTR performance equation. Okay, let's have a look. So it will be V over FA naught is equal to tau over CA naught is equal to X over minus RA. In this case, I know minus RA is equal to K CA to the N, so I'm going to plug in this guy here, K CA to the N, and I want to get it in terms, so let's write XA. I want to write it in terms of X, so if you recall, you don't need to recall it every time, just know it now. It's you have to do this every time. CA is equal to CA naught, 1 minus X. So this will be XA over K CA naught to the N, 1 minus X to the N, or 1 minus XA to the N. All I did is I substituted CA for CA naught 1 minus X. Okay, so now I have this type of equation. So now let's try to let's write it for both reactor 1 and reactor 2, or so if I say V1 over FA naught, and we're being told that the flow rates are the same, so the FA naught does not change, is this equal to XA1 over K CA naught to the N 1 minus XA1 to the power N, and similarly V2 over FA naught is equal to XA2 divided by K CA naught to the N 1 minus XA2 to the N. Okay, so what I'm looking for XA2. So I only have a relation between V1 and V2, so I have this expression. So I'm going to leverage this expression to solve this problem. So if I V2 over V1, this basically means that V2 over V1 is equal to 2. And this is what I'm going to do here. I'm going to rewrite V2 over V1. So if I divide this equation by the top equation, I'm going to get V2 over V1, which is equal to 2, is equal to XA2 divided by 1 minus XA2 to the power N divided by XA1 divided by 1 minus XA1 to the power N. And just be careful, or if you want to know what happened to the rest of these guys. So K CA naught to the N, K CA naught to the N, these two cancelled, and then FA naught, these two cancelled. Okay, so this is what we have, this situation. So I know that XA1, this guy is 0.6, so I can rewrite this equation. Let me clean up this equation here. So this will be equal to, let me just clean it up before substituting anything. XA2 into 1 minus XA1 to the N. So I'm just moving this expression up here, divided by XA1 divided by 1 minus XA2 to the N. So I just, rearranged it to make it, easier to deal with. Instead of having this, 4 floors, just make it 2, right? Okay, let me save this. Let me erase this part here. So I'm gonna just move to the top and solve this problem. Okay, let's use green. So we got to this point, and I know that XA1 is 0.6. So I'm going to substitute XA1, and now this is page 8. Right. So now I have 2 is equal to XA2 into 0.4 to the N divided by 0.6 into 1 minus XA2 to the N. Okay, so I have 3 cases. N is equal to 0.5. So when N is equal to 0.5, I have 2 is equal to XA2 into 0.4 to the 0.5 divided by 0.6 into 1 minus XA2 to the 0.5. And you can use a calculator to solve it, or you can solve it by hand. But just be able to solve these types of problems. Or maybe Excel, you can do it in Excel as well. So in this case, you're gonna get XA2 to be equal to 0.815, okay? And then if I substitute N equals 1, you're gonna get N equals 1 is the easiest one. Or it's the most straightforward one. XA2 will be equal to 0.75. So this is 2, and the third case was when N equals 2, you're gonna get XA2 to be equal to 0.695. Okay, so the main idea is you need to get to this point. If you get to this point, you're 90% there, even more than 90% there, and then It's just math. You can use a computer to do the math for you. It's not a big deal. Calculator, Excel, whatever you want. And if I plug in n equals 0.5, I get xa 2.85. Plug in 1, xa 2.75. Plug in 2, xa2 is 0.695. Okay? So this is number 7. Let me save it. Let me clear. Let's go to the homework and look at the next one. Okay, number 8. An aqueous feed containing A enters a 2-liter plug flow reactor and reacts away. 2A equals R minus RA is 0.25 Ca to the power n. Find the outlet concentration of A for a feed rate of 0.5 mole per minute for n equals 0.5, 1, and 2. So again, I have a feed with an unknown reaction rate, and you need to find the outlet concentration for n equals 0.5, 1, and 2. It's the same exact problem as 7, except I'm using a PFR now. Let's go to the whiteboard and solve this problem. So in this case, I have 9. Okay, and this is problem number 8, right? So in problem number 8, you're being told that you have 2A going to R. You're given the reaction rate minus RA is 0.25. So 0.25 Ca to the power n. It enters a 2-liter PFR, so right, you're being told that Ca naught is equal to 1 mole per liter. Volume is 2 liters. And what else? You're being told a feed rate of 0.5 mole per minute. Okay, feed rate 0.5 mole per minute is a molar flow rate. So Fa naught is 0.5 mole per minute. And what do you need to find? Find the outlet concentration. So you need to find out for n equals 0.5, 1, and 2. So I need to find Ca for n equals 0.5, 1, and 2. Okay. So PFR, let's start with the PFR performance equation. So that is what we're going to do. So PFR performance equation, and it's V over V naught is equal to minus integral Ca naught to Ca of dCA over minus Ra. And I'm using the concentration form because I'm looking for a concentration and I'm given the concentration. I'm not given any conversions. You can, if you want, you can use the conversion form, convert everything to conversions, just whichever you're comfortable with. The math will always work out. Okay, so let's have a look here. V divided by V naught is equal to minus integral dCA over minus RA. Let's have a look at both sides. So on this side, I know that V is equal to 2 liters. V naught, I need the volumetric flow rate. So it's the volumetric flow rate is your molar flow rate divided by your concentration. Similar to like your volume is equal to moles divided by concentration, whatever it is, the same. So in this case, I get 0.5 divided by 1, right? 0.5 divided by 1, so it's equal to 0.5, and this is mole per minute divided by mole per liter. So this will give me liter per minute, right? This is V naught, this is V naught, this is the volume. So V divided by V naught, this expression is equal to 4. Okay, so this is equal to 4, and this is equal to minus integral Ca naught to Ca. I'm going to plug the expression for minus Ra here, which is dCa over 0.25 Ca to the power n. Okay, and let's get rid of these constants. So I'm going to multiply minus 0.25 by 4 and move this negative side to the other side just to clean up this expression. So basically I'm gonna get -1 is equal to integral CA naught to CA of dCA divided by CA to the power n. Okay, sounds good. So now let's solve it for the three cases. So I need to solve it for n equals 0.5, n equals 1, n equals 2. Let's start with the first case here. N equals 0.5, so I have -1 is equal to integral, and again, just remember CA naught is 1, it's given. Integral from 1 to CA, integral of dCA over CA to the 0.5. You know, integral of 1 over 0.5 will be what? CA to the 0.5 divided by 0.5, right? Yeah, from 1 to CA, and this basically equals 2 into, 0.5, we're just moving it to the top, get 2. CA to the 0.5 minus 1, and this is equal to -1. So what am I gonna get? -1, 2 CA to the 0.5 minus 2 is equal to -1. 2 CA to the 0.5 is equal to -1, sorry. So it's equal to 1. So CA is equal to 0.25 mole per liter. Okay, so this is for n equals 0.5. Let me save this. And now let's do it for n equals 1. Did I save it? Yeah, hopefully I saved it. I don't remember. Okay, let's do it for n equals 1. Okay, for n equals 1, for this case I have -1 is equal to integral 1 to CA dCA over CA, and this is equal to minus ln CA, right? Integral of CA is, sorry, ln, right? Integral of 1 over x is ln x from 1 to CA, and this is equal to ln CA minus ln 1, which is 0. So ln CA is equal to -1. So in this case, CA will be equal to 0.367 mole per liter. Okay, this is for n equals 1. And now let's do it again for n equals 2. Okay, let's do it for n equals 2. Boom. N equals 2. So in this case, I have -1 is equal to integral 1 to CA dCA over CA squared, which is equal to CA squared is equal to CA to the -2. I'm going to get -1 over CA from 1 to CA, and this is equal to -1 over CA plus 1. And if I rewrite this, I get -1 over CA plus 1 is equal to -1. So basically 1 over CA is equal to 2. CA is equal to 0.5 mole per liter. Okay, and this is the answer for n equals 2, and this is solution for problem number 8. And again, you just start with your performance equation and you work through algebra. Practice these problems so that you're familiar with the structure of the problem, with the logic of approaching these problems, and you'll be fine. Let me save, let me clear all my drawings, and let's go back to the homework here. Let's have a look at number 9. A liquid reactant stream with an initial concentration of 1.5 moles per liter. And these three are the same as what you've seen in your last homework, right? We're just redoing them for practice. So let's make it good. A liquid reactant stream 1.5 mole per liter passes through two mixed flow reactors in series. The concentration of A in the exit of the first reactor is 1 mole per liter. Find the concentration in the exit stream for the second reactor. Reaction is second order with respect to A, V2 over V1 equals 4. Okay, so I have two mixed flow reactors. V2 over V1 is equal to 4. Initial concentration is 1.5. Concentration in the middle is 1. And you need to find the concentration at the exit. You're being told it's second order with respect to A. Okay, let's go to the whiteboard. I think this is page 11, hopefully. So this is problem number 9. And in this problem, this is a situation, or this is a scenario. I have two CSTRs. And then this goes to a second CSTR right here. You're being told that CA note is it 1.5? Yeah, 1.5. 1.5 mole per liter. And you're being told that the intermediate here, let's call this, so I'm gonna call this 1 and has a volume of V1. I'm gonna call this reactor 2. Volume of V2, I'm gonna call this CA1 is equal to, what is it, 1 mole? Yeah, 1 mole per liter. So CA1 is 1 mole per liter. And you need to find CA2 is equal to what? You're being told it's a second order reaction. Therefore, minus RA is equal to K CA squared. You're also given a piece of information which is V2 over V1 is equal to 4. Yeah, 4. So this reactor is much bigger than this reactor. Right, is equal to 4. Okay, so let's write the performance equation for the PFR. This will be our starting point, or sorry, a CSTR, because they're CSTRs. So your CSTR performance equation is going to be V divided by FA note is equal to tau over CA note is equal to XA over minus RA. Okay. One thing to remember, or let's put a note here. When comparing volumes, you should compare the dimensionless parameter, tau k, right? So tau 1k divided by tau 2k is equal to V1 over V2. And this is what you should use when comparing the volumes. And if you remember on the slide, we had the graph on the left-hand side, it was tau 1k over tau 2k. This dimensionless number corresponds to your volume, okay? So I'm gonna use this expression right here, tau CA note, and let's rewrite it. So I have tau divided by CA note is equal to XA over RA, which is K CA squared. I'm gonna rewrite XA in terms of its definition. So if you recall, XA is equal to CA note minus CA divided by CA note. This is the definition of XA multiplied by 1 over K CA squared. This CA will cancel with this CA, and then I'm going to move this K to the other side. I'm going to move this K here. So in this case, if I do this, I'm going to get basically this expression. So I'm going to get tau K is equal to CA note minus CA divided by CA squared. And I can use this tau to compare the volumes of the reactors. And this is what we're going to do for this case. Let me save this. Let me erase this figure right here. We don't need it anymore. Let me erase this note. And this will be page 12, right? Okay. So I'm going to use this equation to basically determine the outlet composition or the outlet concentration. So let's move up here. So for CSTR1, I have tau 1k is equal to CA naught minus CA1 divided by CA1 squared. Whereas for CSTR2, I have tau 2k is equal to CA1 minus CA2 divided by CA2 squared, right? And if you recall, CA naught was 1.5 and CA1 was 1, right? So this guy is 1.5 and this guy is 1. So I get 1.5 minus 1 divided by 1. So this is what? It's 0.5, right? Yeah, 1.5 minus 1 divided by 1 squared. This is 0.5, and this guy right here will be 1 minus CA2 divided by CA2 squared. I'm going to divide them by each other. So tau 2k divided by tau 1k is equal to, that is equal to what? 3, right? 1 second. Yeah. V2 over V1 is equal to 4. Yeah, so tau 2k over tau 1k is equal to 4, and this is equal to 1 minus CA2 divided by CA2 squared divided by tau 1k, which is 0.5. I cross multiply, so I'm going to get 2 is equal to 1 minus CA2 over CA2 squared. I'm going to rearrange this, so I get 2 CA2 squared plus CA2 minus 1 is equal to 0. And if I factor out 2 CA2 minus 1 multiplied by CA plus 1 is equal to 0. So I have 2 roots. This is not helpful. So this one is here. CA2 is equal to 0.5 mole per liter. Okay, so this is the answer for this problem. Concentration of the second reactor is 0.5. Okay, and again, there's a bit of algebra towards the end. I mean, just polynomials. Just factoring out the polynomial. On the test, the polynomial will be straightforward, so you should be able to factor it out easily. An indication to know if your answer is correct or wrong is just remembering the air concentration. So if you recall, CA naught was 1.5, right? This guy, CA1 was 1. And CA2 is 0.5 in our case. If you solve this problem and you get CA2 to be equal to 2, then your answer is wrong, right? Because CA2 will always have to be less than CA1, right? So the reaction is happening and it's irreversible, so CA2 will always have to be less than CA1. So you could use this as an indicator to gauge, oh, is your answer correctly? Is your answer incorrect? And you should always try to use these logical metrics to try to gauge if your answer makes sense or not. Okay, let's save. Let me clear everything here. Let's go back to the homework. Let's have a look at the next problem. Problem number 10, again, taken from the previous homework. An aqueous reactant stream with a 4 moles of A per liter CA naught passes through a mixed flow reactor followed by a plug flow reactor. Find the concentration at the exit of the plug flow reactor if in the mixed flow reactor CA equals 1 mole per liter. The reaction is second order with respect to A, and the volume of a plug flow unit is 3 times that of the mixed flow unit. So it's similar to the previous one, except now I have a CSTR followed by PFR. I'm given the initial concentration, I'm given the intermediate concentration between them. I'm being told second order, and I'm given the hook between the two performance equations, which is volume of the plug flow unit is 3 times that of the mixed flow. Okay, let's go to the whiteboard. Which one is this? It's number 10. Okay, that's my sharing the screen. Okay, good. Okay, let's This is number 10. I think this is page 13. So for this problem, I have, this is my scenario. I have a CSTR. The output of the CSTR enters a PFR, right? So this is a CSTR. This is a PFR. I'm given that CA note is equal to 4. Yeah, CA note is 4 moles per liter. I'm also being told that the intermediate concentration CA is 1 mole per liter. So I'm being told here that CA, let's call it CA1, is 1 mole per liter. And I'm also given the information that the volume of the PFR is 3 times that of the CSTR. And volume PFR is equal to 3 volume CSTR. Right. What else are you given? Given anything else? Reaction is second order with respect to A, and find the concentration at the exit of the plug flow reactor. Okay, so I need to find CA2. You're also being told that the reaction is equal to second order with respect to A, right? So let's solve this problem again. So I have 2 things. I have a CSTR and I have a PFR. So and I have this ratio of volumes, which is what I'm going to use. So logically, if I'm going to use this fraction, or basically if I'm going to rearrange this fraction, rearrange this piece of information to write V PFR over V CSTR is equal to 3. If you recall, this basically means that tau PFR K over tau CSTR K is equal to 3. So I'm going to use the performance equation of PFR and the performance equation of the CSTR to get these 2 parameters, put them here, solve this to get CA2. This is the logic which we're going to follow. So let's start with the performance equation for the CSTR. If you recall, CSTR performance equation, we said it's tau over CA naught is equal to XA over minus RA. And if I write the definition of XA, which is CA naught minus CA over CA naught, and I write the equation of RA, which is right here, which is 1 over K CA squared. And this is exactly what we did during the last problem. CA naught cancels with CA naught here, and I'm going to move K to the other side to get the performance equation for the CSTR, which is tau CSTR K is equal to CA naught minus, so in this case, let's write it. So in CA, in this case, we're using notation 1. So let's call this 1, let's call this 1, minus CA1 over CA1 squared. Now let's plug in the numbers since we have them. So CA naught is 4, CA1 is 1, CA1 squared is 1 squared, so this is equal to 3. This is the performance equation for the CSTR. Okay, let's do the same for the PFR performance equation for the PFR right here. If you recall, tau is equal to minus integral of CA1 to CA2 in this case, because the inlet is CA1, the outlet is CA2, of dCA over minus RA, and this will be minus integral CA1 CA2 of 1 over K CA squared. And what I'm going to do is I'm going to move this K to the other side. So I'm going to get tau PFR K is equal to minus integral of CA1 to CA2 of 1 over CA squared, and integral of 1 over CA squared is what? Minus 1 over CA, so this is equal to minus 1 into minus 1 over CA from CA1, sorry, to CA2. The minus cancels with the minus, so I get basically 1 over CA2 minus 1 over CA1. And I'm just going to plug CA1 here because it's 1. So basically this is equal to 1 over CA2 minus 1. So I have my tau PFRK, I have my tau CSTRK. I'm going to combine them I'm going to combine them using this expression to solve this problem. So if I do this, let's see if we can do it in this space here. Oops. If I, it's ugly here. Let's try to do that. No, it's not working out. Anyways, if you combine them, you're gonna get 3 is equal to, or is it 3 or is it, yeah, it's 3. 3 is equal to, plug flows 3 times, right? Yeah, it's fine. Tau PFRK, we said is 1 over CA2 minus 1 divided by tau CSTRK, which is 3, right? And you get basically 9 plus 1 is equal to 1 over CA2. So CA2 is just 0.1 mole per meter cubed. Okay. Yeah, so this is the type of problem you should expect to get. And yeah, this is the type of problem you should expect to see on the test as well. And this is the solution. Again, it's not really complex. Just go through the procedure, understand the logic, go through it slowly. Should be able to get it. So I'm going to save the slide. Let me clear everything, and let's go to the homework and do the last problem. So last problem is problem number 11 in this case, and this is going to show up as well. So 10 and 11 are the types of problems you should, 100% one of them will show up, okay? Practice it. Reactant A plus R, or sorry, A goes to R in this case. Let me insert this symbol right here. Symbol, there we go. Reactant A goes to R, Ca naught is equal to 16 mole per meter cubed. Passes in steady flow through 4 equal-sized mixed flow reactors in series. Tau total equals 2 minutes. When steady state is achieved, the concentration of A is found to be 11.5 to 1 intermediate in the intermediate reactors. For this reaction, what must be the tau plug so as to reduce Ca from Ca naught 26 to CAF equals 1 mole per meter cubed. Okay, so you need to find the equivalent space-time to, you need to find the space-time in a plug flow to achieve the same conversion in the CSTR. And this relates to what we talked about. This relates to what we talked about in the slides, and we talked about this in the previous homework solution. I think this is 14. In the previous homework solution, basically you need to relate the equation for CSTR in series to the equation for a PFR, right? And for a first order, which is the case we're really focusing on when dealing with this type of scenario, for a first order, for a first reversible reaction, CSTRs in series are represented using this equation. Ca naught over CAF is equal to 1 plus K tau I to the power n. And if you recall that tau I is equal to tau total over n. And you know, in the last when solving the previous homework, I drew the diagram, we did everything, so you can really watch it there. And for a PFR, so PFR, again, for a first order reversible reaction, CAF over CA naught is equal to exponential of minus K tau. Okay, so what do we need to find? I need to find this tau, which corresponds to this performance. So what I'm going to do is I'm going to use this equation to solve for K, plug this K here, get this tau. Okay, this is really the approach from doing this problem. So let's focus on this side. So we're given CA naught to be 26, CAF is 1 plus K, tau is equal to 2 divided by 4, right? So you're being told that the overall space-time for the 4 reactors is 2 minutes. So this is equal to 0.5 minutes. So it's equal to 1 plus K, 0.5, and is 4. So if you do this calculation, you're going to get, actually CA naught is 16. Yeah, I changed this to make it easier to calculate. Okay. CA naught is actually 16. So if you do this, if you take the 4th root of 16, you're going to get 2, right? So you're going to get 2 is equal to 1 plus K to the 0.5. So K in this case is equal to 2, right? 2 multiplied by half is 1, plus 1 is equal to 1. And again, it's the first order reaction, so the units is the second minus 1. So now I have this K, I'm going to take it to this side. On this side, I have CAF, which is 1 divided by 16, is equal to exponential of minus 2 multiplied by tau. So in this case, tau is equal to minus ln of 1 over 16 divided by 2. And the number I got for tau, let me calculate it, I didn't calculate it actually, is 1.386 minutes, right? And this is the tau, PF or tau plug, whatever you want to call it. And this is the answer to this problem. So this, I think, concludes the homework, right? Let me have a look. Yeah, this is it. Please go over these problems. Make sure you know how to solve them. If you don't know how to solve them, come to office hours, ask me, but at least make sure you know how to. If you're able to solve these problems and you're comfortable with the homework, your exam will be very easy for you. But you know, make sure you cover everything, and please reach out if something is not clear. Thank you so much.